So video will cover section 4.6, as Mr. Peru said, graphs of other trigonometric functions. So far we have covered the graph of sine, the graph of cosine, and so now it's the turn of tangent. After that, we will cover cotangent, which is very similar to tangent, but instead of having asymptotes that are at negative pi over 2 and pi over 2, the asymptotes for cotangent will be at negative pi and pi. And another thing that they have different is that the graph will look like this. But we'll get to that one in a minute. So now let's focus on tangent. So we did a little group activity where we graphed that on the board, and we know that the asymptotes are going to appear anywhere where the cosine is equal to 0. And so we have that here, and you can see that those asymptotes happen to be multiples of pi over 2. But they're not just multiples of pi over 2. They happen to be odd multiples of pi over 2. So what do I mean by that? Is that this one right here is actually 3 times pi over 2. 3 is an odd number, so then that's how you get 3 pi over 2. Now, the even multiples of pi over 2, such as, let's say, pi, that is actually an x-intercept, not an asymptote. So, for example, if I say 2 times pi over 2, that will be an even multiple of pi over 2. So if I multiply that, I will get 2 pi divided by 2, which is equal to pi. So for that reason, any multiple of pi over 2 that will be of this form, even, will be on the graph represented as an x-intercept. And you guys did very good at finding those on the graph that we constructed. Are we clear with that? What is an odd multiple and an even multiple? Yeah. Okay. So let's go back to what's written here. And so, do you guys remember what was the period for sine and cosine? 2 pi. Very good. So for tangent and cotangent, it will be pi. The domain, what was the domain of sine and cosine? All real numbers, is that? For tangent, it will be almost all real numbers, but we're going to exclude where those asymptotes happen, which will be odd multiples of pi over 2. So all real numbers except odd multiples of pi over 2, and that's what we have here as asymptotes. The range happens to be all real numbers. Okay. I would say something like x such that x does not equal n times pi over 2. And n is odd. Now, if you want to get fancier, you could say n is not divisible by 2. Or no. 2 does not divide n. 2 does not divide n. That's another way you could say n is odd because it cannot be divided by 2. When I learned this type of notation in college, I was really confused because they will tell us the denominator first. And I was like, what? But yes, it's true. You could use that. But I think that might be an option. I think that might be an option on my math lab. But that's a good question, Sean. So now we're ready to talk about the asymptotes, every odd multiple of pi over 2. And so since those are vertical asymptotes, it makes sense that we exclude them from the domain, correct? Right? Because the tangent is undefined there. Now, the x-intercepts, like I was telling you, those occur midway, or the midpoint between each 2 consecutive asymptotes, just like you guys found them over there. We have the odd, tangent function is odd, and it looks like a cubic function, right? And so it is symmetric with respect to the origin. Meaning that if you look at our graph, or let's look at the one here actually. We have this point here at pi over 4, comma 1, and we also have this point at negative pi over 4, comma negative 1. All right? That is how you determine symmetry with respect to the origin. Okay, and what I was telling you about those key points that I just happened to mark here on the graph, I told you the book refers to those as points happening 1/4 and 3/4 from one asymptote. So this will be, if this is your asymptote here, and this is your second asymptote, we can find a key point 1/4 right here, and 3/4 from this asymptote. This will be like 1/4 and 3/4. Right? So that's what they're referring to. I personally like to think of it this way. I have two asymptotes consecutive. In the middle, I will have an intercept. And then in between the first asymptote and the intercept, I will have one of those key points. And then in between the intercept and the second asymptote, I will have another key point there. So it's all about midpoints. Just keep taking your midpoints. All right, so remember I told you the asymptotes pi over 2 and negative pi over 2, we're going to be using those. And we're going to use that when we're graph a transformation, which is what we're going to do next. And to find those asymptotes, we're going to construct two equations. One will equal pi over 2 and the other one negative pi over 2. So let's get started. This can actually be done quickly. At 4:50. Even if I don't finish, you guys will have to finish the lesson on video. I really cannot. We have to do at least 2 sections per week. What is it? The exam, whenever we're done with 4.8. I think it goes all the way to 4.8.
So when, like, so after next week?
7, 8. I'll let you know for sure on Tuesday. Yeah. Okay, so we need to find those vertical asymptotes. Let's get started with that quickly. So we're going to take this part, and this is a 2, by the way. And so we take that x over 2, and we know that the two asymptotes are going to be between pi over 2 and negative pi over 2. So now what I'm going to do is create the two equations. One will have the negative pi over 2, of course, and the other one will have pi over 2. And now I'm going to solve for x. So this 2 down here is dividing to the x. So if I take that across, it's going to multiply. So we will have negative pi over 2 times 2. And so that will be negative 2 pi over 2. That equals x. And so that will become negative pi. So that will be the first one of our vertical asymptotes. And I think you guys can kind of infer where the next one will be. What do you guys think we're going to get? Pi. Well, let's see if it's true. So we take this 2, of course. Oh, not that one, this one. Move it across, so we will get x is equal to 2 times pi over 2. And so that will be x is equal to 2 pi over 2, which will turn into just pi. So when we graph our function, we have, of course, 0 will be at the y-axis. And so I'm just label my point. I'm going to label my points to my convenience. So I'm going to say that this is pi, this is negative pi. And if you notice here, they're asking us to graph from negative pi to positive 3 pi. So maybe this is not going to work. So that will be negative pi, and then positive pi, 2 pi, and 3 pi. All right. So let's go ahead and graph the asymptotes. Where do you guys think the next one will be? Would it be at 2 pi or at 3 pi? 3. At 3 pi. Very good. Okay. So they have to always be spaced. The space between asymptotes will be consistent. Okay? Now, in between every two asymptotes, what do we have? Intercept. So right here, intercept at 2 pi, intercept at 0. Now, remember those key points that I was telling you guys? Yeah? Those will happen midway between asymptote and intercept and asymptote. What value will go here? Not over 4,
2.
Over 2. And what about the one on the right side?
Pi over 2.
Pi over 2. Wow, you guys are so smart. Now, remember how when we were graphing sine and cosine, we were looking at the amplitude, right? If it was vertically stretched. And that we knew because of this number right here. So that number is also going to change the y value of our key points because it's multiplying the y value by 2. All right? So what I mean is that right here, instead of graphing the key point at negative pi over 2, comma, negative 1, we will use negative 2. So negative 2, and here we will go to positive 2. Let me write the coordinates here. So it will be negative pi over 2, comma, negative 2, and the other one will be pi over 2, comma, positive 2. And then we connect it like almost like a cubic function. And remember, the range is all real numbers, so it does make sense that we have arrows on both ends. All right, and that's it, because we were only asked to graph from negative pi to positive 3 pi. So let's move on to the next graph. Any question? Not yet? All right. Okay. Now right here, what we have is just going to be a little shifting horizontal to the left. But we're going to graph it the exact same way. So we're going to take what's in here and say that our asymptotes will be between pi over 2 and negative pi over 2, and we're going to do the exact same steps. So we're going to create those two equations, one with the negative and one with the positive. And that will tell us where our first two consecutive asymptotes will be at. Alright, so remember, we are solving for x. So I'm going to take this pi over 4 to the other side, so it's going to be subtracting. So now x, we need to change to the same denominator, so that would be fourths. So negative pi over 2, if we change that to fourths, how many fourths do we have? 2. And they're negative. So negative 2 pi over 4. So negative 2 pi over 4 minus pi over 4 will be negative 3 pi over 4. So that will equal to x. So that's where one of our asymptotes will be. Now the other one, could you guys tell me, what do you guys think? What do you guys think it will be at? That's actually a very good guess. But keep in mind, we had a horizontal shifting. So I will recommend that we still do the equation to make sure, okay? So x will be pi over 2 minus pi over 4. So then x will be, if we turn pi over 2 into fourths, that will be 2 pi over 4 minus pi over 4. So x will be equal to, how many pi over 4? Just pi over 4. See? So if we didn't have that horizontal shift and we were kind of like starting at 0 with an intercept, then yes, we could infer that it will be the asymptotes are opposites. But in this case, they're not. So let's go ahead and graph them. And it just say to graph, two full periods. Oh, that's not straight. Okay, go ahead with that. So, pi over 4. Pi over 2. What will be next? Telescope, negative direction, so this will be negative pi over 4, negative pi over 2. The next one will be negative 3 pi over 4. And I think we could squeeze 2 periods there. I don't think so. We're going to need a little bit more space. Could you get them? Okay, so I'm going to start by graphing those.
Miss Bethan's room. They want to speak with you.
Would you? I wasn't recording. Can you guys hear? Okay, so take a look at this problem. If you need to pause the video, please. Karina, we're talking to you. So yeah, we did this to find the asymptotes, and then we found them here. And so those are the dashed lines. Halfway between the asymptotes are the x-intercepts. And then halfway between that, we have our key points that you can see here and here, here and here. Okay. So cotangent again. So I was saying that cotangent will be undefined whenever the sine is 0. And so that will happen at any multiple of pi. And not just any multiple, but integral multiples. What does that mean? Integral. They're multiples, but like, think about this. If I say 1.5 times pi, will that be an integral multiple?
Yes. No? Okay.
What does that word remind you of?
Integers?
Integers, yes. So those will have to be integers that are multiples of pi, such as 2 pi, 3 pi, 4 pi, or also on the negative side, or just negative pi, simple. We're going to use the same process as we did with tangent. And if you notice, one of the other differences between tangent and cotangent is that they are reflected. So instead of being, the tangent function is, the parent function is increasing. Look at the graph on the dry erase board. That one is increasing if you read it from left to right. And if you look at the cotangent, it is decreasing. You guys notice that? Okay. All right. So I know you're all looking at the clock.
Yes.
Stop it. So I'm going to do this super quick. I will take that 2x and create an equation that equals to pi. So that will be pi over 2. And then I will take 2x and create an equation that says that equals to negative pi. Why am I choosing pi and negative pi? Because that's where the regular asymptotes will happen. Not the regular ones, but the ones of the parent function. So now for this one, I will graph it just like I was graphing the tangent. Now remember, the parent function, the asymptotes happen at pi and negative pi. The reason that for the graph they changed is because we had that 2 here. So that 2 is causing a horizontal shrinking. So instead of having the asymptotes that spread apart, they will be here. Again, intercept in between, and the key points will be reflected like that. Oh, actually, they should be at 3 and negative 3. Let's just make that a negative 3, and that is a 3. Problem fixed. All right, next graph. And actually, this is the last thing, the graphs of cosecant and secant. And so, I'm going to leave the homework for the section open until Thursday, but I'm going to finish teaching this after you guys leave, all right?
Okay.
But pretty easy because I know you're not going to watch the video, but I'm going to throw some random comments in there.
Do we have to write down these random comments?
I don't know, am I asking?
Well, what if we forgot? Like,
Could be a question on the test.
Really?
Okay, so just so you know, if you know how to graph sine, and you are very good at it, then there's no way you will fail at graphing cosecant. Because whenever sine has an x-intercept, such as here, what happens with cosecant? If sine is equal to 0, what will the cosecant be?
1.
Not 1.
0.
No, it will be undefined. So that's why we have those asymptotes there. No, that will be sine. Okay. So then what happens here is that whenever the sine has a maximum, you will just draw type of like a parabola shape there, and that's it. Whenever sine has a minimum, you do the same. Just like that.
That looks pretty easy.
Yeah. So easy. So for cosine, it will just be the reciprocal of, for secant, it will be the reciprocal of cosine. And that's it. So for your homework, guys, make sure you do look over what are the domain and range. I'll try to explain in a video, but make sure you do watch at least the last 2 slides of section 4.5 because you will have word problems on the test. So let's go over the period, domain, range, vertical asymptotes, and to see if it's odd or even. So by definition, the sine function is said to be an odd function. So if the sine function is an odd function, then cosecant is also going to be an odd function. We did go over this identities before, but just so you, in case you forgot. The period will be the same as the sine function. It will be 2 pi. And we can see here one complete period of the graph. It will be from here to here and then here. That will form a complete period. Now the domain is all real numbers except for the integral multiples of pi. And so the reason we exclude those is because at those multiples of pi, we are going to have vertical asymptotes. So it makes sense we exclude those from the domain. The reason we have to exclude them is because if the cosecant for those particular angles is undefined. And that is because cosecant, as you can see here, is the reciprocal of sine. So whenever the sine is equal to 0, the cosecant will be undefined. And that's what I was talking about, those x-intercepts on the sine graph. So when we talk about cosecant, instead of being x-intercepts, they become vertical asymptotes. Now, what we're going to do here, well, for the range, let's go over that before we start graphing. The range is going to be all real numbers such that the numbers will be less than what the minimum for the sine function will be, or greater than what the maximum of the sine function will be. Now, if we break that into an interval, what we're talking about are numbers that go from here, the y values, to here, or from here. Can you get the door, Julie?
Yes.
To here. So either they're greater I'm just going to write it. So they are greater or equal to 1, or the y values are less than or equal to 1. Now let's move on to the secant function. And just so you remember, secant is the secant of x is the reciprocal of cosine. So what we can see here is that whenever the cosine, and what you see graph here with the dash curved, that one, that is the graph of cosine. So if you can see, whenever cosine has an x-intercept, like such as there, here and here, here and here, the secant graph, whenever the cosine equals to 0, the secant will be undefined. And so for that reason, we're going to draw vertical asymptotes there. Now, if whenever we have a cosine having a maximum value, we're going to draw that parabola-shaped graph. Whenever cosine has a minimum, then we will trace that. Now let's look over period is the same as cosine. The domain in this case will be all real numbers except for odd multiples of pi over 2. So here we're talking about numbers like negative 5 pi over 2, negative 3 pi over 2, negative pi over 2, of course, also pi over 2, 3 pi over 2, and so on. So those will be the odd multiples of pi over 2. For the range, remember, we're talking about the y values. So the y values will be anything that is greater or equal to 1, or anything that is less than or equal to negative 1. So remember, we're talking about those y values. So they're going to be pretty much everything except for those numbers that are in between here and here. And now, just like the cosine function is an even function, the secant function will also be even. And you can tell here that it is symmetric with respect to the y-axis. Now, let's graph a couple of those. And first of all, we need to graph 2 times the cosecant of 2x. Now, I already have the graph for 2 times the sine of 2x. Now, let's just review this quickly. And the reason the period for this graph changed to pi is because of this constant right here. So remember, to find the period of sine, I'm speaking of sine, the sine wave, you divide 2 pi by the constant, which happens to be a 2, and that's how we get pi. And so that's the reason for the cycle to be completed from 0 to pi. Now, the amplitude also changed a little bit here because of this constant here that is multiplying all the y values by 2, which is causing a vertical stretch. So the amplitude is 2, the minimum will be at negative 2, the maximum will be at 2. So now we are going to graph this one, and what we're going to do is trace some vertical asymptotes anywhere where we see where the sine graph has an x-intercept. So that will be here. Also here, that's an x-intercept. Here we have another one. And here. And now, just to trace our graph, anywhere where the sine graph has a maximum, we will trace something that looks like a parabola. And remember not to get close to the asymptotes. You can get close and not touch them. Right, so that will be a good picture of our graph. Okay, and so this is the end of the video.